Okay, today we are going to start chapter 16, which discusses concepts of heat transfer from a hotter object to a colder object. There are three, or I should say, from hotter substances to a colder substances. There are three ways in which heat can be transferred uh, between hotter matter and colder matter. One of them is conduction, which occurs from contact with the between the hotter object and the colder object. The other one is another one is convection, which involves the circulation of hotter air through or into colder air, which equalizes the temperature between the two and heats up the colder air. The third one is radiation uh, transfer, and this does not require any direct contact between the hotter object and the colder object. Example is when the sun is shining and heats up the interior of a car on either a hot day or a cold day. In either case, the radiation from the sun enters through the windshield and is absorbed into the leather or plastic or material in the inside the car. This will also cause heating, which is from the sun in this case, but there's no direct contact between the sun and the object. It is simply transferred from radiation. Uh, the last 2 points that we will go through are Newton's law of cooling, which states how uh, uh, the a hot object can become cooled down in the presence of cold air, or one in which we will have, for example, um, a cold object placed inside the oven, and the rate at which the object heats up will be proportional to the difference in temperature between the surrounding air and the food inside the oven. And the last one we'll talk about is the effect uh, of the heating of the Earth by means of what's called the greenhouse effect. And this is a radiation transfer of heat from the sun. And as we know, that heat gets trapped in the atmosphere and unable to reflect or let uh, the, uh, the, the heat from the Earth escape back into space. So we'll talk about different these different mechanisms in the chapter that we have ahead of us. Now, in this slide, we're going to reiterate the concepts of conduction, convection, radiation by stating that in any of these cases, two objects that are of different temperatures but in thermal contact with each other will tend to reach a common temperature in one, two, or three of the following ways. These methods are, as we said before, conduction, convection, and radiation. And typically, the temperature that they will reach, which is in common, will be between the temperature of the hotter mass and the colder mass. And we'll discuss how these occur and how this energy transfer or heat transfer takes place. Now, the first method that of heat transfer we'll talk about is conduction. It's one that perhaps we are most familiar with, and that occurs when the objects, in this case the feet of the individual, are either in contact with the grass or in contact with the concrete. Now, an example would be on a hot summer day in which the concrete reaches a higher temperature than the grass because it has a lower specific heat capacity. And therefore, what happens is that the foot on the person's left foot begins to feel the effects of the heat from the hotter bricks or cement than is felt from the grass. In this particular case, what's happening is that the jiggling of the electrons in the um, from the atoms or molecules in the concrete are causing increased jiggling of the electrons in the feet of the individual, and that is felt as heat or as an uncomfortable hot temperature when that thermal contact occurs. And in this case, it is also physical contact. That is to say that the concrete is in direct contact with the feet, and the energy is transferred by the collisions or the excitation or the velocity of the electrons in the concrete, which cause increased velocity of the electrons in the feet, therefore causing the experience of heat to occur. Now, objects that absorb heat quickly are called good conductors. That is to say that they have a low specific heat capacity, which means that for a given amount of heat, you'll get a much higher temperature rise than you will for insulators. Insulators will be the opposite of conductors, and they do not absorb heat readily, and therefore we call them insulators. Now, the property that makes a good conductor good is that these substances will have loosely held electrons in their orbits around the atoms or the molecules, and they will be able to quickly transfer their kinetic energy to the electrons in the other material that they're in contact with. And so if the conductor is if the material is a conductor, then placing it in contact with a hot object will cause it to heat up much more quickly. And these materials that are good conductors of heat are also good conductors of electricity for the same reason that the electrons are held very loosely around their atoms. They're easy to dislocate from the atoms and for them to act as free electrons and to jiggle around and move quickly with kinetic energy not being bound to their particular atoms. So the examples you see here, which are silver, copper, gold, aluminum, etc., will be examples of good conductors because they have loosely bound electrons, and they not only conduct heat very quickly, but they also conduct electricity, which is the flow of electrons, because they have electrons that are free to move in the substance. Now, objects that are poor conductors have their electrons tightly bound to the atoms or molecules that they originate from, and therefore their electrons cannot absorb the kinetic energy or obtain the kinetic energy due to the heat transfer. Examples of these are glass, wool, wood, paper, plastic foam, and air. Another good example of this is the down jackets, which are stuffed feathers from birds that form very warm jackets because they do not absorb the heat from the body, and therefore the heat from the body is trapped within the jacket. And these form very good insulators, and therefore they make very good winter coats. So in this question, you're asked to consider what would happen if you hold one end of a metal bar or a knife, for example, against a piece of ice. And the end of, in this case, one finds that the end that of the bar or the knife that is in your hand will soon become very cold. So the question is, does cold flow from the ice to your hand? Well, the answer is that cold does not flow from an object to another object. Rather, heat flows from one object to the other object. So in this case, what we say is that the knife or the metal bar loses heat because it is in contact with a colder material, which in this case is ice, and therefore the um, the the electrons in the metal knife or bar are imparting their kinetic energy to the electrons in the ice. And because of this happening, then what happens is there is heat flow um, from the knife into the ice, which will cause the ice to warm up. But the reduction in heat or the expulsion of heat from the metal knife causes it to cool down. So we don't say that cold flows from one object to another. Rather, it is the heat from the hotter object that is being extracted to the material that is at a colder temperature. So the answer is no, it does not. And you'll see that in the next slide as well. Now, in this slide, we iterate or reiterate or discuss the fact that insulating materials, what we call insulation, such as the fiberglass that is placed between the interior walls and the exterior walls of a house, um, is an insulator which slows the transfer of heat from the warm house to a cold exterior in the wintertime. So it doesn't prevent the flow of internal energy, which in this case is the internal energy of the air molecules in the house, but it slows the rate at which that internal energy flows to the outside world. And therefore, that's the property that makes it a good insulator. And similarly, for a down jacket filled with the bird feathers that have a very high, good insulation, um, also slow the rate of heat loss from the body to the outside world, and therefore keeps us quite warm. Now, another example of an insulator, a very good insulator, are red hot burning coals, which are laid upon the ground. As you see here, the person walking is able to walk over the red hot coals. It could also be wood embers as well, since wood is a good insulator as well, and therefore it does not transfer heat to the foot of the person walking over them. And in this case, as long as he walks at a fairly good clip or pace, um, he will not his feet will not get burned because the heat cannot be transferred from the insulator to the person's foot. So now we discuss the second method of heat transfer between substances. In this case, we assume that we have two fluids that are initially separate from each other. One would be, for example, a hotter mass. In this case, a hotter mass of water at the bottom of a boiling of a pot over the stove, and the colder the colder water above the at the top layer of the pot is going to be at a colder temperature. But eventually, the temperature of the hot water in the bottom will equilibrate or cause heating of the colder water in the top by means of mixing. And that mixing can occur either by forcing the water in the bottom, such as stirring it to mix with the colder water, or there could be natural processes where the colder water is naturally going to, I'm sorry, the hotter water at the bottom is naturally going to rise to the top because it's less dense, and the colder water, which is more dense, falls to the bottom. In either way, there's a circulation of the two fluids so that when I turn off the heat, they will achieve an equilibrium temperature throughout the container or throughout the volume of the water, assuming that there is no other heat transfer from the air, for example. So this is an example of convection, um, and we can have other examples such as the rising mass of thermal air from the earth, which is heated from on a hot day by the sun, say over the desert, and that as the hot air rises, it begins to mix with the colder air above it and cause the heat transfer to that colder air. Another example of convection heating of a mass of air, it can be observed from the smoke from a fire, which rises and blends with the surrounding cooler air, therefore transferring its kinetic energy to the to the colder air, and therefore cause heating of that colder air above the level of the fire, and that smoke can rise over many tens of meters to cause the heating to occur well above the surface of the earth. The other example that's shown here is the one we just talked about, which is that the warm air, for example, as we said, on the surface of the desert on a hot day, becomes less dense and becomes, therefore, is rises upward, and the higher density air, which is colder, sinks down, and there is a mixing of the cold and hot air to increase the temperature of the cold air above the surface. Now, convective warming of the air surrounding air can also be seen from the example of a pressure cooker on top of the stove that is being heated by the flame. And in a pressure cooker, the lid is firmly attached to the pot so that the only escaping steam can occur through a small orifice on the top of the lid. As the heating occurs, some portion of that steam begins to be forced out of the pressure cooker, and that forced air then begins to cool the air that is surrounding the cloud of steam. And as you can see in this example, that cooling effect is very noticeable because the steam that is coming out of the cooker at 212 degrees, which is too hot to touch, is not too hot to touch when placed at a distance of several inches above the orifice of the pot. And so this convection cooling can be seen in this case as well. Now, in this example, you are asked to look at a situation where you have warm air in the valley of a parcel of land, and you can have very high elevation mountains right next to that valley, such as might occur at Denver, for example, where going west just a few miles will reach into mountains that are thousands of feet higher than the elevation of Denver. So the question arises is that if the warm air is rising, um, then why do the mountaintops stay cold with their snow cover, while the valleys below are relatively warm and green? In other words, why doesn't that warm air cause the warm air cause the snow on the mountaintops to melt, since that warm air rises? Well, there's a couple examples to look at. One is, does warm air cool when it's rising? Well, yes, it does. So the warm air leaving the surface of Denver will be much higher. I'm sorry, that temperature, that warm air will be have a much lower temperature by the time it reaches the elevation of the mountain peaks and right next to Denver. So there will still be a large temperature gradient. Uh, Secondly, we've learned that air is itself an insulator, and so that means to say that it is very inefficient or it has a relatively slow rate of thermal energy transfer due to its insulating nature, and therefore that's going to slow the heating of the from the valleys up to the mountaintop. So the answer to this is that both A and B are true. They both help maintain the low temperatures on the mountaintop. Now, the final example of convection that we are going to cover, and this will be the last slide for this lecture, and the end of the convection section. Where in this case we are going to consider the sea breeze that occurs as a result of convective heating of the air, or we should say uneven heating of air over the land versus over the water. So this would be, for example, sitting on the coast of an ocean breeze. We could be on the California coast, for example. And the basic idea here is that when the sun comes out during the day, there's a heating of the surface. And the heating of the surface is very uneven in that the heating of the land causes a larger temperature rise than the heating of the water. And this is because water has a very high heat capacity, as we've discussed before. And as a result, the temperature of the surface of the water does not change nearly as rapidly as the surface temperature of the land. Now, once this occurs and we get a higher temperature on the land, then the air on the surface that's in contact with the land will be heated up by the land and begin to rise because it will be less dense and it will begin to rise vertically. And you see the arrows going in the upward direction right above the land. As this happens, the cooler air from the sea rushes in to fill that void, and the circulation of air in the daytime occurs from an onshore breeze, which brings the air from the ocean directly over the ocean, directly over the land, and we have a breeze that is pushing inland. This is exemplified and magnified by a campfire that you can see in the figure, where the smoke is now being blown towards the land as a result of the sea breeze that occurs because of the uneven heating of the air masses over land versus water. Now, at nighttime, the opposite effect occurs, namely that the land will cool down much more rapidly than the water. The water temperature doesn't budge significantly. And so now what happens is we have more heating of the air over the water than we have over the land. So the air over the water is going to rise upwards, and the colder air from over the land is going to rush in, and therefore we get an outward sea breeze, or a breeze that is pushing outward towards the ocean. And that is also visible by the smoke from the fire that is now being blown towards the ocean in the nighttime period, as opposed to towards the land in the daytime period. And this circular motion then causes convection to occur because the warmer air will eventually descend down to the surface over the land, and therefore it will um, be heated up by the air surrounding the land, and we get a convective heating of the air over the land in the nighttime periods. And so this is exactly what happens here. And another example we might consider is which is not a natural process, but there is a convective a device called a convective stove, or I'm sorry, convective oven. And the way a convective oven works is that the fan blows the air over the hotter regions of the stove to cause the circulation of the air in the oven so that it all mixes at a uniform temperature. There is no temperature variation within the air mass that is inside of the oven. So convective ovens work in a similar way, that they cause mixing between the hot air and cold air, and therefore uh, heat up the colder air and bring it to this equal temperature of the warmer air.